Assalamu alaikum, dear student. Now we are in week number 7 and this is the lecture number 1 of week number 7. So today we are going to start a new chapter, that is dimensional analysis. This chapter will cover part of the CLO3, the course learning objective number 3. So first of all, we will see what are the learning objectives of this chapter, and after completing this chapter you should be able to apply the Buckingham Pi theorem. You should also be able to develop a set of dimensionless variables for a given flow situation, and you should also be able to discuss the use of dimensionless variables in data analysis, and finally you should be able to apply the concepts of modeling and similitude to develop prediction equations. So to achieve such objectives or goals, the topics we are going to cover in today's lectures are the dimensional homogeneity and units, and we will perform some of the practice problems related to above topic. And after complete understanding of dimensional homogeneity and units and doing some practice problem, we will see what is dimension analysis, why do we do dimension analysis, and what we achieve by doing dimension analysis, and what are the techniques we use to perform dimension analysis. And after that we will see one of the method of dimension analysis, which is Buckingham Pi theorem, if the time allows, in today's lecture. So let's see what is dimensional homogeneity and units. So we know fluid have variety of characteristics and it can be described qualitatively and quantitatively. The characteristics means the fluid properties as well as the fluid flow properties. Okay, so that can be distinguished qualitatively and quantitatively. So what is the qualitative characteristics and what are the quantitative characteristics? So the qualitative characteristics identify the nature or type of the fluid characteristics, okay, such as length, time, stress and velocity and so on. Okay, so this type of characteristics describes the flow properties and the fluid properties. So what is the quantitative characteristics? The quantitative characteristics provides a numerical measures, okay, of the qualitative characteristics of fluids. It requires both numbers and standards by which various quantities can be compared. Okay, so here it is very clear. Basically this qualitative characteristics only provides the type and nature of the fluid characteristics. Okay, the type means whether it is fluid properties or flow properties. Nature means the properties are fundamental properties or the drive properties. Okay, we will see in the later part, but this we understand. So here only it provides the name and nature, okay, the flow properties or the fluid properties. But here because these properties are the physical properties, so physical properties must have magnitude, okay, so that indicated with the numbers, and also these numbers should be explained by using some standards. Standards means the standard of units, that is SI system, CGS system, FPS system. So these numbers must be explained with some standards. Okay, so here a standard for length might be a meter or foot. Okay, for time an hour or second, and for mass a slug or kilogram. Such standards are called units. Okay, so the qualitative characteristics such as length, which is indicated with L, okay, the time, which is indicated with T, the mass is indicated with M, and the temperature, it is indicated with theta, can also be termed as primary quantities. Okay, these characteristics are called the primary quantities or the fundamental quantities, and they are also known as basic dimensions or fundamental dimensions. Okay, so these characteristics are termed as fundamental dimensions or the basic dimensions. Okay, and the primary quantities can be used to provide qualitative characteristics of any other fluid characteristics. Okay, some other fluid characteristics can also be derived by using the primary quantities or the primary characteristics. Okay, such as, and these characteristics is termed as secondary quantities or derived dimensions. Okay, secondary dimensions, secondary quantities, or derived quantities or derived dimensions. Okay, for example, area. Okay, area is derived from the fundamental or basic quantities, which is length L. Okay, so fundamental quantities are the quantities, or the fundamental dimensions are the dimensions that cannot be derived from any other quantities. Okay, they are unique. Okay, so these fundamental dimensions cannot be derived from any other quantities. Okay, but the derived quantities can be achieved or gained by using the primary quantities or the fundamental quantities. Just like area can be achieved by using length. Velocity can be derived by using length and time. Okay, density can be used by mass and length. Okay, and so on is also termed as derived dimension. Okay, so here you can see some of the fundamental dimensions. There are 7 fundamental quantities or the fundamental dimensions. Okay, so what are they? Just like length cannot be derived from any other dimensions. Okay, mass cannot be derived from any other dimensions. Okay, dimension do not change. Okay, dimensions, the dimensions do not change by changing the system of units. Please keep in mind, the dimensions do not change by changing the system of units. Dimensions remain same. Okay, if it is length remains same, doesn't matter it is in feet, it is in meter, it is in centimeter, the length is remain length. Okay, same, the mass remain mass, whether it is slug, whether it is kilogram, whether it is pound mass. Okay, it will remain mass. Okay, so the dimensions remain same. Okay, so here the temperature, it is indicated because since we are using the symbol for the time is capital T, so we are not using capital T, but it is used in many places, so we are using theta here. Okay, to indicate the temperature. Electric current we are indicating with I. Okay, luminous intensity we are using I. Okay, the intensity of light basically. Okay, so amount of substance, that is mole. Okay, that is indicated with N. So these are the fundamental quantities that cannot be derived from any other quantities. Okay, any other fundamental quantities, it cannot be derived. Okay, so here you can see many physical quantities or the derived physical quantities or physical dimensions, physical quantities or the other derived dimensions or dimension of the other physical quantities. Okay, so the derived dimensions are given in FLT system and MLT system. What is FLT system and MLT system? FLT system means when we use force as a fundamental quantity. Okay, so force, length into time, or we can use mass as a fundamental quantities. Okay, mass into length into time. So we can convert mass into force in this system, and we can convert force into mass in this system. So we have mentioned here, if you convert the acceleration in the basic dimensional form, so that can be written as just like acceleration is equals to what is the unit of acceleration is meter per second square. So meter is indicated with the length and time is square is indicated with the t, because this is the symbol we have here. Okay, so since we are using capital M, not a small m here, so please keep in mind mass we are using capital M instead of small m. Okay, so here the unit of acceleration is liter per second square, so if you take it up it's going to be -2. Angle, okay, angle, because it is you can see it is 0. Okay, so theta. Okay, so angular acceleration is omega square. Okay, 1 over f 2 pi f. Okay, and here the area L square, the density is mass per unit volume. So here you can see in MLT system the mass will come straight away mass and divided by volume cube, that means length cube. But in the FLT system you have to convert mass into force. Okay, so what is mass equals to? So in that place you have to convert mass into force. Okay, so mass is equal to F is equals to ma. So if you convert change to other side, put the unit of force. Okay, so you can convert in this way, F is equals to ma, so you can convert F force indicated with F divided by a means L over L multiplied by t minus 2. Okay, so when you bring it here to the other side, so finally you will end up with this equation. Okay, so here the energy, you know what is energy, basically is the work done. You can take it force into displacement. So this is force. In FLT system force will directly indicate with the F, because the symbol of force is F multiplied by displacement, that is L. But if you convert in MLT system, so you have to convert force into mass. Okay, so if you convert, force will be equal to m into a. So m is equals to m or multiplied by L into t minus 2, that will be equal to force. Okay, the F will be equal to mass m into L into t minus 2, that will be equal to F. So in that way you can convert mass into we will see in the some examples we will see. So here are the some physical quantities or the derived dimensions which are mentioned here, that can either you can memorize or either you should know how to derive these dimensions of the physical quantities, how to write down the physical quantities in the form of dimensions. Okay, so this is basically written the dimensions, physical quantities in the form of dimensions in the system of FLT system and in the MLT system. Okay, so let's see and do some example. For example, verify the dimensions in both FLT and MLT system of the following quantities which appear in table 1.1. Okay, number 1, the volume we have to verify, that just now we have discussed, and we will verify what we will calculate from here. We have to verify acceleration, we have to verify mass, we have to verify moment of inertia, the area, and work. So these 5 quantities we have to write down in the form of FLT system and in the form of MLT system, and verify these dimensions with the table 1.1. So let's see. The volume we know, that is L cube. Okay, so the volume will remain whether it is MLT system or FLT system, because in the volume there is no component of mass or the force. So the volume will remain same in both the system. Okay, so if there is a component of mass or force, so it can be changed in the 2 different systems. But since there is no component of mass and force in the volume, so the volume will be the dimension of the volume will be same in both the system. Okay, the acceleration, in the acceleration also we do not have any component of mass and the force. So the acceleration will also be same in both the system. That will be equal to, acceleration will be equal to what? Time rate of change of velocity. So the velocity is equal to length per unit time. So LT minus 1 divided by time. So it will go up, so it will become LT minus 1. Okay, so the mass will be equal to M. Okay, in the system of MLT. But in the FLT system, mass will be equal to what? Force. We know that force is equals to ma, so the mass will be equal to force divided by acceleration. So force is replaced by F divided by L T minus 2. So when you will take it up, so L will come up, so it will become L minus 1, and the T minus 2 will change into T plus 2. So the mass will be equal to, in FLT system, will be equal to F L minus 1 and T minus 2. Okay, so the moment of inertia is basically the 4th time of area. Okay, so L square into L square will become L4. So there is no component of mass here. Okay, so there is no component of mass here, so it is also remain same in both the system. So work we know that it is force into displacement. So in the FLT system, the work will be equal to FL, but the same work will in MLT system will be equal to, we know that the work is equals to force into displacement. So the force in the form of mass is equal to this MLT minus 2. So we replace this F with MLT minus 2 multiplied by L. Okay, so when we multiplied with L, what will happen? This L and L become L square and T minus 2. So that will be equal to ML square and T minus 2. So if you go and verify for the dimensions in MLT and FLT system, you can verify in the previous table that we have done. Okay, so here you can see the mass is equal to FL minus 1 T square. You see that we have drive, and mass in the MLT system is M. Okay, and same here you can see the acceleration. You can see LT minus 2 in both the system is same. You can see the volume here. You can see the volume here, L cube and L cube. Okay, you can see work here. You see in the FLT system the work is equal to FL, and when we converted it into the MLT system, the force is equal to, you can see the force. Okay, the force is equal to, in MLT system, MLT minus 2. So when you multiplied with L, so it will become L square T minus 2. So this we verifies. Okay, so this is how we change the physical quantities in the form of dimensions. Okay, in the form of dimensions, and we verified that. So now we do one more exercise. So here the force F of the wind blowing against a building is given by F is equals to CD rho V square A by 2, where V is the wind speed, rho is the density of air, A is the cross-sectional area of the building, and CD is a constant, then the drag coefficient. So basically it's a drag coefficient is a dimensionless number. Okay, it has no dimensions. So determine the dimension of the drag coefficient. So technically we know the drag coefficient and it has no units. So when we will end up with this solution, so we should end up with a dimensionless number. Okay, so let's see here. So drag coefficient is equal to the force, the drag force is equals to F is equals to CD rho V square A by 2. Okay, so we have to determine the CD, the dimensions of CD, as we have a dimension of S we know, dimension of density we know, dimension of V square we know, and dimension of, since the force is given F. Okay, so it is better to consider FLT system. Okay, if most of the units in which if M is given, so we will take MLT system. If in most of the unit is M is given, so we will take MLT system. Okay, so here you can see, here we have a force F, the building is given by V square and area. Okay, so we can and the density is given, and density is also is given in the equation. So the choice is yours, because either you take MLT system or FLT system, because in the MLT system it is easy to write down the mass time length cube, and here they used MLT system, but you can use FLT system and you will end up with the same result. So if you use F, you don't have to change F, just change the density with the FLT system. So instead of F you will get instead of M you will get F here. So you can replace, but here they are using MLT system, so replace F with MLT minus 2 and replace F with the dimension of density, replace V square with the dimension of the velocity, replace A with the dimension of area. Okay, and when you solved all the equation, so you will finally get the power of M is equals to M naught, L is equals to L naught, T is equals to T naught. So all has a power is equals to 0, so which indicates that it has no units. All the dimensions have the power 0, which means it CD is a dimensionless number. So now let's see the law of dimension analysis, or the principle of homogeneity. What is the principle of homogeneity? So it states that the equation is dimensionally correct. Okay, if you develop any relationship between the variables, okay, because you see, what is the equation? Equation is the relationship between the different variables. So if you develop a equation, if you determine a equation, or if you develop a relationship between different variables, so this equation is dimensionally correct if the dimensions on the left hand side of the equation are equal to the dimension on the right hand side of the equation. If not, the equation is not dimensionally correct or possible. So that means if you develop a equation, if the dimension of left hand side is equal to right hand side, that means that equation is true, that relationship is possible. Okay, that relationship is correct. But if the dimension of left hand side is not equal to dimension of right hand side, so that means the relationship between the variables you have developed or you have found is technically correct, and which is technically not possible. Okay, and in other words, we can also write down the principle of homogeneity also states that the power of a fundamental dimensions. Okay, what are the fundamental dimensions? M, L, T, theta, that is current, all 7 fundamental dimensions on both side of the equation will be identical, 4-dimensionally homogeneous equation. So the meaning is same. Okay, if the dimension of both the sides are same, or the power of the fundamental dimensions are same or identical on both sides, that means the equation is possible, the relationship between the variables are possible. So here we can check what exactly it means. So here you can see there is a equation which says that velocity is equals to half gh square. So let's see this statement is correct or wrong. So apply the dimensional homogeneity principle. So change, so what is basically velocity? Velocity is equals to length over time, half, what is g? Half is the constant, so we are not considering here at all because it has no meaning. So g, what is g? Gravitational acceleration, L over t square, what is h is the height, L square. Okay, so when we simplified that, this is going to be L cube over t square, so L over t square. So that means you see the terms do not match. The dimension of the left hand side and the dimension of the left hand sides are not matching. Even the power, this is L is the fundamental dimension, T is the fundamental dimension, but the power of the fundamental dimensions are also not matching. It means this equation is technically wrong. This equation is not exist. The relationship between these variables, the velocity, the gravitational acceleration and height, is technically, this relationship is not possible. This is not right equation. Okay, so here we write down V is equals to under root GH, a equation we have wrote. So let's see this equation is true or not. The velocity, whether the velocity is equal to GH or not. So V is equals to L over T, and here is equals to L over T square into L. Okay, so when you simplified that, finally you see, so these two terms are dimensionally equal. The power of the fundamental dimensions are equal. So here the terms match. This could be a valid formula. So this can be we can rely on the relationship between the variables are correct. So based on that, now we can see one we can do one exercise. So here you can see the volume rate of flow, the volume flow rate through a pipe containing a slowly moving liquid is given by the equation. So this is the equation is given. Okay, so where R is the pipe radius, del P is the pressure drop along the pipe, mu is the fluid properties called viscosity, and the unit is given, the dimensional unit is given, and L is the length of the pipe. So what are the dimensions of the constant pi by 8? Okay, would you classify this equation as a general homogeneous equation? Explain. Okay, so we have to find out the equation of this constant. Okay, we have to find out the equation for the constant. So constant has no dimensions. Okay, so we are going to separate this pi by 8, and we are moving all the variables to the other side. So if the dimension, the final dimension of the whole unit is equal to a constant, or there is no dimensions, that means it is true. Okay, so let's see, we substitute the value of all the units. Okay, the radius is the length, del pressure is force per unit area, okay, that we can find out in the dimensional list. Okay, and the mu, the viscosity, the dynamic viscosity, length is given. So when you simplify that, so finally we end up with you see L cube T minus 1, L cube T minus 1. So they're going to be cancel each other. So pi by 8 will be a dimensionless number, and the equation is generally homogeneous. So this equation is true. Q is equal to this, could be equal to this equation. So, and the equation is general homogeneous equation that is valid in any consistent unit system. Yes. Okay, so now let's see what is dimension analysis and why do we do dimension analysis. So this chapter teaches the technique used to correlate the experimentally measured data. It means that the dimension analysis technique is mainly used in research and development section or department that mainly every company has. So whatever the new product or the component they develop, they has to test. Okay, so for example, if they want to test a component or a phenomena in a real life condition, okay, in a real life condition, such as the phenomena, they want to test an aeroplane to fly with a particular velocity in the space. Okay, so what is the drag force offered by the air to the plane that we have to calculate? Or if you have developed a car, it is moving with a particular velocity, what would be the drag force offered by the air to the car? And also, if you have developed a submarine flowing underwater with a particular velocity, so what would be the drag force offered by the water to the submarine? Or another case, suppose if you have developed a new pipe, okay, so what would be the pressure drop if the water flow through that pipe, if some other liquid will flow that pipe? So if you want to find out the pressure drop through the pipe, so you need a testing facility or requirement. So if you are doing this test in the lab or in the wind tunnel, okay, so to achieve the real life condition, to apply the real life condition, in that case you have to find, first of all, you have to find out the variables at which the drag force or the pressure drop in pipes are depending on. Okay, so if you are dealing with the variables may be variables are dependent variables and independent variables. So to develop a relationship between the dependent and independent variables, definitely you have to use the dimensional homogeneity technique or the principle of homogeneity, which is very important to verify the relationship between the dependent and independent variable. So here we are considering a case, okay, of a water flowing through a circular pipe. So consider a steady flow of an incompressible pipe, or the fluid is Newtonian fluid, through a long smooth walled horizontal circular pipe. Okay, so an important characteristics of this system is the pressure drop. Okay, the pressure drop per unit length. Based on this pressure drop calculation, basically we calculate the size of the pump. Okay, so whatever is the pressure drop of the pipe, based on that we would be able to calculate the size of the motor or the size of the pump, okay, along the pipe as a result of friction. In the real life condition, definitely there is a pipe and there is a friction, and because of the friction there is a pressure drop, and that pressure drop can be overcome only by using the pump. Okay, so so the pressure drop per unit length can only be obtained by using the experimental data. Okay, so if you find out the pressure drop, so what we can do, we can verify the data by using some experiment. So what we can do, the first step is in planning the experiment is to determine the factors or the variables that will have an effect on the pressure drop per unit length. That includes pipe diameter and the fluid density, fluid viscosity and fluid velocity. So definitely if any factor will change, the pressure drop will change. Okay, definitely the pipe diameter have an effect. If you change the pipe diameter, the pressure drop will vary. If you change the type of the fluid, so the density of the fluid, the pressure drop will vary. If the viscosity is changing, the pipe friction loss will vary. If the velocity will change, definitely the pressure drop will vary. So these are the variables which basically affects the pressure drop per unit length. So first of all, you find out the independent variables that affect the friction loss per unit length. Now the mathematical relationship between the pressure drop and the above factors is unknown, okay, because we do not have any relationship between these two factors. So we are going to perform an experiment, is unknown and can be obtained through experiments, okay. So the experiment will be performed by changing one variable while holding the other variable constant, okay. What we can do, only one variable we can vary and we can change the behavior, okay. If we change the velocity, so how the pressure drop is varying. If you change the density, then how the pressure drop is varying. So at a time only we can perform by varying one variable, okay. So such as, because if we will vary 2 or 3 variables together, what will happen, we cannot observe this change is happening because of which variable, okay. So in that case we have to vary one variable and keep the other variable constant, okay. So such as the pressure variation is observed by changing the velocity, keeping the other variable constant, okay. So here first you keep the velocity is 1 meter per second and diameter is 1 meter per second. So that means 1 meter per second for 1 meter diameter of pipe. After that 1 meter. So here a series of experiment will be performed and the data will be recorded for different velocities, okay. So the experimental experiment will be repeated by varying the other variables, okay. So we will keep 1 meter per second, then we will vary the diameter, then we will vary the viscosity. So this will take much long time and there is a lot of paperwork, okay. So if one experiment you perform for 1 meter per second, if you take 10 or 15 measurements for one variable, you can understand how much time you needed. So this approach is used to determine the relationship between the pressure drop and the various factors that influence the pressure drop. So finally we combine all the major data to obtain the relationship between the pressure drop and diameter, density, viscosity and velocities. So here you can see the velocity is varying and density, velocity is varying, density and the viscosity is constant. So this is only the velocity is varying, so you can understand. So velocity is equals to 1 meter per second, 2 meter per second, 3 meter per second, 5 meter per second, and everything is constant. So you can understand this one data will take how much time to you, okay. But and you cannot take the velocity for, if you take the diameter, for example 1 meter, it's 1 inch diameter, you have taken 1 inch and then you have taken another variable, okay. So that is dia is varying, okay. So this is the velocity graph for the 1 meter diameter, 1 inch diameter. So if the diameter is varying, so velocity is what, 1 meter per second, okay. So that means this you will take, if you want to calculate the varying diameter with a different velocity, you need 100 of graphs. For this you need 100 of tables. For another observation, for another experiment, you need, if you want to vary the density, you need 100 of experiments. So this will consume lot of time and efforts, and error may be include, okay. So here it illustrate the plots showing that the pressure drop in the pipe may be affected by several different factors, okay. So if you have done, for example, the calculation for diameter of 1 meter per second, diameter of 1 inch, 2 inch, 3 inch, 4 inch. So if you want to find out the graph for the half inch pipe, what is the pressure drop? So what would you do? So that means even then you cannot do the experiment so precisely, but even then, since you have no choice, so this is the only way you have to do the experiment and make the relationship between the variables. So here the experiment can be simplified by forming non-dimensional combinations or of variables called dimensional, okay. So to avoid, okay, Okay, so to avoid such experiments and long time, maybe the varying one variable for one diameter, it will take 1 day, okay, or couple of days. So you can imagine if you are varying this experiment for different diameter, 100 up to 10 or 15 diameters, so how much time it will consume. Okay, so what we do to avoid such experiments and time consumptions, the experiments can be simplified. Okay, we can avoid this experiment and we can simplify it by forming a non-dimensionless combination of variables called dimensionless product or dimensionless group. So this is the power of dimensionless number. So we can avoid this such big experiments and we can perform some dimensionless group or numbers, okay, that can provide you the value of pressure drop for any diameter, for any velocity, for any density or any viscosity. For example, these are the two dimensional groups we form with the variables we have previously considered. These are the variables. So by using the dimensionless dimensional analysis technique, we develop two dimensionless numbers, okay, group from the 5 variables. Now instead of doing experiments with 5 variables, we vary one dimensionless group and see the variation in other dimensionless group. For example, you can see that this dimensionless group is a function of this group. Okay, so if you vary, so here you can see this is the graph. Okay, so this is the two dimensionless group. Okay, both are dimensionally homogeneous. So if you vary diameter, if you want to find out the pressure drop for diameter 1 inches, so just put all the factors are known, okay, because this is known, this is known, this is known. If you want to change the diameter, okay, so just everything is known, change the diameter will be equal to this factor. So everything is known, okay, so you can calculate pressure drop. If you want to change the viscosity for any type of fluid, for any diameter, for any velocity, for any density, okay, this one curve is enough. You don't have to plot thousands of curves to calculate the pressure drop. Okay, so just one curve, one page is enough to calculate the pressure drop for any diameter of pipe, for any velocity passing through the pipe, for any density of fluid and any viscosity of fluid. This one paper, one curve is enough. So this is the power of the dimensionless group or dimensionless numbers. Okay, so we develop the dimensionless group by considering the dimensions of the variables involved. Okay, so as we know that the physical quantities are described in terms of 3 basic dimensions: mass, length and time. Okay, normally we use these three basic terms: temperature, the current, then we use based on the phenomena and the cases. An alternative set of the basic dimension is the force, length and time, MLT system and FLT system. Okay, so the notation is used indicate dimensional equalities. So this is basically for the dimensional homogeneity or equalities we use this symbol. So dimension of the variable in the pipe flow rate. So what are the dimensions of the variables that flow through the pipe? So the variables which depends on each other, the dependent variable is delta P, and independent variables are diameter, density, viscosity and velocities, and these are the dimensions of these numbers. Okay, so put these numbers, put these dimensions in the dimensional group. So when you will, so this is the first group, this is the second group. So when you will put them all and when you simplify that, you will end up with this number. This is a dimensionless number. This is 0, this is 0 equal to 1, 1, 1. So this is a dimensionless number. So when you put this all dimensions in this equation, so you will end up with F0, L0, T0. So that means this is also a dimensionless number. So that means left hand side and both hand side are dimensionally homogeneous. Okay, so the technique reduces the number of variables from 5 to 2. So what is this technique? This technique, before we have 5 variables, now we reduce 5 variable to 2 variables. So if you want to vary any variable, you can vary and you can calculate the other dimensionless number, and based on that you can calculate the required value that you want to calculate. Okay, so what we call this technique is reduce the number of variables. Okay, so the new variable are dimensionless group, so any system of unit can be used. So if you use any system of unit, okay, SI system, FPS system, okay, but the dimension doesn't change, okay, the length remain length, foot remain length, meter remain length, okay, so it doesn't matter which system of unit you're using, it will not change. Okay, so this type of analysis is called dimension analysis. And to find out the dimensionless numbers, the method or technique that we use, that is called a Buckingham Pi theorem, and is used for the dimensional analysis, that we will discuss in the next lecture, inshallah. So this is end of the today's lecture.